So it's been long enough since I did my last video on the science behind Minecraft, and admittedly, the original Minecraft video was way more about the science and using Minecraft to explain it. So this time, how about I actually look at the science behind something from the game? Hello everybody, and welcome back to another episode of The Science Of, the show where I slowly overanalyze your favourite game shows and more. Today, we're back in Minecraft to take a look at the science behind Minecraft's second most useful block after the crafting bench, the furnace. Now, this might seem like a bit of an odd topic, but there's a surprising amount of interesting science behind this generic and pretty simple item. And make no mistake, this item is incredibly simple, and you'll be crafting it time and time again as you explore caves, get lost, and then keep exploring, get some ores, and then think, damn, this pickaxe is almost broken, I need some more iron. And eventually, you'll end up at the bottom of a mineshaft with a ton of iron, 2 forgotten furnaces, and only your bare hands to punch your way back to the surface. But, did you know that before the furnace's introduction in Minecraft 0.31, you could only smelt items by dropping them on the ground and burning them with a flint and steel? That's kind of crazy, right? Something that we now only use for the express reason of burning down forests or getting rid of waste items was once the only way of getting a classic iron hoe. But it's been a long time since those early 2009 smeltings, and a lot has changed. For a start, furnaces used to only be craftable from cobblestone, but now we can make them from deep slate, cobblestone, blackstone, all the stones. So today, we're going to look into the science and a bit of the history behind these furnaces to see just how accurate the Minecraft furnaces are to their real world influences. And to be fair to Minecraft, we're not just going to scream about it being unrealistic for slight inaccuracies. It's a sandbox game that released in 2011. I'm going to give it some slack. Let's start by looking at some of the basics of the Minecraft furnace, specifically what it's made from. The Minecraft furnace has a variety of known recipes, but no matter what, we're looking at some kind of stone, cobblestone, deep slate, etc, etc. Ye old Middle Ages blast furnaces were pretty simple, being only about 3 meters tall and made of rocks. These blast furnaces involved iron, limestone and charcoal being fed in a hole through the top, with air blast being blown up through the lower section with bellows. This is the first important difference between the Minecraft furnace and the real world ones. You see, both of these furnaces are made out of stone, but with the Minecraft furnace, only iron ore goes in and iron ingots come out. This means that the fire inside the furnace needs to reach about 1538 degrees Celsius, the melting point of iron, in order to produce that pure iron ingot. And given that the Minecraft furnace can also be used to turn sand into glass, it will also be required to reach temperatures as high as 1600 degrees Celsius. And you see, there's a wide range of melting points for different types of stone, with felsic materials such as quartz and granite having melting points as low as 600 to 700 degrees Celsius, and mafic materials such as basalt having melting points of between 1100 and 1400 degrees Celsius, far below the melting point of iron. In fact, pretty much all minerals that you could find will be molten at temperatures of 1200 degrees Celsius. Does this mean that the Minecraft furnace would simply melt before it got hot enough to melt the iron ore? Absolutely not. This is a simple fact that could very easily be overlooked. Furnaces aren't ovens, they're glorified fire pits. The heat in a furnace comes from a fire, and fires are hottest at their centre, cooling down the further away you get from them. For example, imagine you have a campfire and you want to cook on it. You don't stick the food in the centre of the fire because it would get burnt by temperatures of around 900 degrees Celsius. Instead, what you do is you place the food just above the fire in the thermal fume, where temperatures will be around 320 degrees Celsius. But then again, our Minecraft furnace is slightly more like a pizza oven, with a slot at the top for the ore and a slot at the bottom for the fuel. So who knows, maybe the top will get hot enough to completely break down. Let's take a look at ancient furnaces to compare. Ancient civilizations made a type of metallurgic furnace called a bloomery. These were made out of clay and stone chimneys. The smelting process involved a bed of red hot charcoal mixed with iron ore, with more charcoal added for heat. The ore was chemically reduced by the charcoal to produce metal iron. But this wasn't molten iron that could be easily worked with. Instead, it was a spongy mass of pasty globules. Through repeated reheating and hammering, you could remove a lot of the waste products and get the wrought iron product that was much easier to work with. But in Minecraft, what we are seeing are iron bars being formed from the iron ore, without the furnace being damaged. This suggests that the iron is being melted or softened, then formed into bars that can be used for crafting. This would require the melting point of the iron to be reduced so that the Minecraft furnace doesn't melt. So how would we do that? Well, to discuss how we can lower the melting point of our iron more clearly, we're first going to have to shove together some hydrogen and oxygen and look at water. And I swear this is leading somewhere, so stick with me. You see, water, or more specifically ice, your best friend in summer, is a nice simple way to explain the concept of metallurgical flux. If I were to ask you at what point water turns into ice, I'm sure most of you would tell me that water freezes at 0 degrees Celsius or 32 degrees Fahrenheit. But what if I were to ask what is the freezing point of a saturated salt solution? Water containing so much salt that adding any more would lead to small deposits at the bottom of the bottle. Well then we'd be looking at temperatures that are significantly lower, with freezing points of saltwater solutions being somewhere around minus 21 degrees Celsius. And that's not even mentioning the other extreme with purified water. I'm talking incredibly pure, only hydrogen and oxygen atoms allowed. This water will supercool to temperatures as low as minus 38 degrees Celsius before it absolutely must start forming ice crystals. Pure water is a liquid at room temperature. Its molecules have enough kinetic energy to move and flow over each other freely. As you cool these molecules down, they lose their kinetic energy and become less volatile. Eventually, they'll have no energy and then will reside to resting. These resting molecules will tend to form very specific hexagonal patterns, forming crystals similar to those I explored in my video on the science of Banjo-Kazooie, and these crystals will then go on to form solid ice. Now, water does not form one big old crystal of ice, no. It has what is known as a polycrystalline structure, formed of many tiny hexagonal crystals that will come together to form a large slab of ice with many separate distinct domains of hexagonal crystals separated by grain boundaries with extra space between the crystals. Well, most ice looks like this, but if you can somehow get the ice crystals to form perfect sheets of these hexagonal crystals, then it is possible to get completely clear ice, but that is incredibly tricky. Now, is all this to say that water doesn't freeze at 0 degrees Celsius? No, of course not. You can go to your kitchen and put some water into a freezer at 0 degrees and come back, and there will be ice formation. But even as the molecules slow down with the temperature changes, it is very unlikely for them all to spontaneously arrange themselves into the correct pattern to form ice as soon as the temperature falls below 0 degrees. In fact, only a small group of these water molecules will form themselves into these ice clusters that will form a nucleus of ice within the liquid. Now, if this nucleus is too small, it will just dissolve into the water, but if it's large enough, then it will attract more water molecules surrounding it to form a larger nucleus. In purified water, this nucleation almost never happens unless the temperatures fall well below the freezing point as mentioned earlier. But if the water has small impurities, then the initial phase of nucleation gets assisted, with a few ice molecules finding the correct ice-like arrangement more easily. These impurities can be many things. In your tap water, they're normally just minerals that have dissolved into the water through the pipeline or water filtering plants. This doesn't work with the purest of H2O, there is no nucleation point, but what can you do? Well, you can simply lower the water to about minus 2 degrees or so, and at this point the purified water will still be able to flow fluidly over itself as you would expect. But if you then shake the water to disturb the surface, creating tiny air bubbles or air pockets, these will act as nucleation points. Once you get that crystallization, it will act as a new nucleation point for the formation of ice crystals, and before you know it, you've got a bottle of solid ice. Now, this might be a bit confusing to you, as I mentioned earlier that the saturated salt solution would only freeze at around minus 21 degrees. This water has salt to act as nucleation points, so why wouldn't it freeze just as easily as tap water? Well, you see, the salt has a bad habit of blocking the water molecules from packing together when the temperature is lowered, which prevents the water from crystallizing and forming ice. This can't happen forever though, and at some point it is going to get cold enough for the ice to form, but it is a hell of a lot lower than you would expect. And this brings us back to our medieval Minecraft furnace, because believe it or not, there is a lot we can learn about the smelting of iron from melting ice. We now know that the process of crystallization and how to use these impurities to reduce the freezing temperature of water. but like a lot of things in chemistry, this can be reversed, and we can add stuff to our iron ore in order to reduce its melting temperature. This stuff has a name, and its name is Flux. Flux is a broad term referring to substances introduced in the smelting of ores to reduce their melting temperatures, promoting fluidity and removing objectionable impurities in the form of slag. The most common flux used in the smelting of iron were limestones, with other flux including silica sand, the stuff that glass is made out of, dolomite, borax and fluorite. But we've already seen how bloomeries can produce this raw iron. What about using a stone furnace to produce glass? Although we've shown that the melting point of glass can be as high as 1500 degrees Celsius, you can get glasses whose softening temperature are as low as 600 degrees Celsius, perfect for our Minecraft furnaces. Common household glass is mostly formed of silicon dioxide, the same chemical found in quartz, and it's more commonly found in a polycrystalline form, sand. This is pure silica, and it has a melting point of 2000 degrees Celsius. Sodium carbonate, on the other hand, has a significantly lower melting point of around 1000 degrees Celsius, well within what's possible for our Minecraft furnaces. But this soda is problematic as it makes the glass soluble, and that's not going to keep your Minecraft build safe from the rain. This can thankfully be fixed by adding in lime or calcium oxide, which restores the insolubility of the glass. This results in a glass that melts at 1000 degrees but can be worked with and formed in temperatures as low as 700 degrees Celsius, which is much more useful for building. This makes our Minecraft furnace more than capable of making glass panes and blocks. The only problem we have now is figuring out how the hell Minecraft's furnace will get to those temperatures, when only 1 stone of coal is needed to smelt 8 blocks of meter by meter volume solid glass, which is a whole other problem, but let's leave it at that for today. So, as you would expect for an open world sandbox game released in 2011, the furnace doesn't represent a large amount of what's been shown in this video, with no need for Flux to melt down your iron ore into iron ingots. There's no need to overcomplicate a simple crafting system, but as of Minecraft 1.17, the furnace system did add something that made the whole system a bit more realistic. As of Minecraft 1.17, a new item was introduced called raw iron, replacing iron ore as the item you pick up when you break a block of iron ore without silk touch on your pickaxe. Now there is something you may notice about this item compared to the old block of iron ore. The iron is looking a lot redder than it used to, and this isn't a surprise, with iron oxide, more commonly being known as rust, being distinctly red. Now unfortunately, this iron ore still has a melting point that's way too high for our poor stone furnace to manage, but if you had enough time, patience and the right flux, you could feasibly lower their melting points to a point where it's below the melting point of the stone. But let's face it, that's a lot of work, and there are easier ways to get around that. If we took some of the clay surrounding the riverbanks and turned it into a forge like the bloomer mentioned at the beginning of this video, then we'd have something. Owing to their high bond strengths, ceramics have a much higher melting temperature than stone, with most ceramics having a melting temperature above 2000 degrees Celsius, which is more than suitable for our iron forge. So there we go. Minecraft's furnace isn't the most realistic thing in the world, but this could definitely be argued as just a simple limitation of Minecraft's crafting system. And of course, this isn't the last time I'm going to return to blocks and buildings. I still need to look at the science behind creepers. And I've always been curious as to how strong Steve would need to be to carry around a 4th dimension crushing inventory full of shulker boxes holding diamond blocks. As always, if you enjoyed this video, then don't forget to leave a like, comment and subscribe to the channel. And if you want to help combat the ever-changing and frustrating YouTube algorithm, then make sure you share the video to help my channel grow. If you have a particular scientific subject or topic that you'd like to see me cover in the future, then please tell me in the comments down below. As well as that, follow me on Twitter to get updates on the latest science of videos, and join my Discord for chats about science, gaming and more. But until next time, this has been the Science of Minecraft. I'll see you next time. Thanks for watching. If you're looking for more game-based content, then you can join me over on Twitch, where I livestream 3 times a week, playing all manner of games suggested by the community. Or if you want to support the channel even further, you could also contribute to my Patreon, where you'll get behind the scenes access to the creation of all videos, as well as access to my private Minecraft server.